For this video, let's try to have here the parametric form of a straight line path. Or we are going to provide here the expression that would stand for parameterizing a straight line path. Now here, this is actually in general straight line path. If we have here horizontal or vertical path, line path, we will have actually another form for that. But generally, if we're going to have here the straight line path, we are going to use this parameterization later on. We have here if your path C is a straight line. Okay, and take note of this because this is unique for this situation. From any point, okay, let's say Z sub 1 to Z sub 2. Okay? A linear parameterization, works best in this form. Z of t would be equivalent to your Z sub 1 plus t times the difference of your Z sub 2 and Z sub 1. Whatever would those values would be. Okay? Take note, this is what we need because to solve for the integral of your complex function f of z along your path C, you will have here the integral from a to b of your f of z of t. This one here. Then multiplying it with the first derivative of your z of t with respect to t. Okay? So that's what you're going to use for your solution later on for the complex integral. That we have here additional condition that your t is between 0 and 1. Therefore, this would be your A and this would be your B. So you're going to use whatever your Z sub 1 and Z sub 2 would be, and that would be this form here for your parametric form for your solution to be solvable. By the way, there is a good question here. Will A and B always 0 and 1? Now, this is just for convenience. Okay? This is the suggested value for your A and B. The reason for that is when we parameterize a path, we describe how a point, okay, moves along it using your variable t. That's why we will have z of t instead of your original function in terms of z, which that t acts like your time. For a straight line between 2 points, t usually goes from 0 to 1. Because it's the simplest way to represent movement from any starting point, which you can say t at 0, towards your ending point, which is t at 1. But of course, it's not all the time 0 and 1. That's just a convenient choice. You could use any interval that increases from the start to end. You could even have here 0 to 5 or 0 to 2. It's up to you. The only difference here is how fast your t runs through the line, but it doesn't change the path itself. The convenient way to solve that or to come up with a solution which is similar to all or most convenient to be used is actually if it's 0 to 1. Basically, it's just the concept of movement from a certain point A at 0 or t equal to 0 and t equal to 1, which is your B. Okay? So the choice of 0 or 1 is just for convenience. Any interval would work, but 0 to 1 keeps the parameterization simple, consistent, and easy to compute for all of the line integrals. Okay? So, but this is again specific for your straight line path. If the path is not straight line, therefore we will have another parametric form. But this is good for that. And if you have some examples later on, you can actually look for. Let's have here an example. Let's illustrate an example. Let's say we are solving the integral of a certain function from along the straight line path from your z sub 1, which is 0, to your z sub 2, which is, let's say, 2 plus I. That's just an example. So the formula earlier for your z of t, okay, is equivalent to your z sub 1. So you have z sub 1 plus t times the difference of z sub 2 and z sub 1. So you will have here your z sub 1 is 0 plus t times 2 plus I minus 0. So you will have here 2 plus I of t. This is your z of t that you need to plug in this one here. Okay? on whatever your function is. If your function is, say for example, a quadratic function, so you're going to plug in that given function. At the same time, you could also take here your additional requirement for your complex integral, which is your z prime of t. And of course, with respect to t, this will be treated as constant. That's just a value of 2 plus I. So basically, you will get your parametric form of your z and its first derivative. You're going to plug that in here in your function times the derivative with respect to t. Get the integral from 0 to 1. That's the complex integral of your function along your straight line path c. We'll have another video for other paths which are not straight line. Thank you very much for watching.